Self-capacitance is a measure of the ability of an object to store an electric charge. Self-capacitance is a function of only the geometry describing the storage of electric charge. A material with a large self-capacitance stores more electric charge at a given voltage than a material with low self-capacitance. This is the equation for self-capacitance. It depends upon the charge on the conductor and the change in electric potential between the surface of the conductor and a position infinitely far away from the conductor. Let's explore this definition further by determining the self-capacitance of a conducting sphere. The first step in this calculation is to determine the potential difference between the surface of the conductor and a position infinitely far away from the conductor. This involves an integration of the electric field of the conductor. We can determine the electric field using Gauss's law and assume that the conducting sphere carries a net charge Q distributed uniformly across its surface. The limits of integration of the electric field are from the surface of the conductor, a distance r from the center of the conductor, to infinity. Several terms in this integration are constant and can be taken outside the integral. The remaining integral is straightforward and gives the following result. We can then use this expression to determine the self-capacitance of the conducting sphere. As expected, the self-capacitance depends upon only geometric factors of the conductor. In this case, it depends upon the surface area of the conductor, 4 times pi times r. The larger the surface area, the larger the self-capacitance. A capacitor is a device that stores a separation of electric charge. The mutual capacitance, or simply the capacitance, of the capacitor is a measure of the ability of the capacitor to store a separation of electric charge, and thus to store electric potential energy. Mutual capacitance is a function only of the geometry describing the separation of the positive and negative charges in the capacitor. This is the equation for mutual capacitance of a capacitor separating charges plus Q and minus Q. It depends upon the positive charge stored in the capacitor and the difference in electric potential between the positive and negative charges in the capacitor. Let's explore this definition further by determining the mutual capacitance of a parallel plate capacitor. The first step in this calculation is to determine the potential difference between the two plates of the capacitor. The separation of electric charges on the two plates of the capacitor can be created by applying an external electric field to the two plates. This separation of electric charges creates an electric field between the plates of the capacitor. It is this electric field that stores energy, since it is associated with the separation of electric charges. The next step in the calculation is to integrate the electric field to determine the electric potential difference between the two plates of the capacitor. The electric field can be determined using Gauss's law. The magnitude of the electric field is constant and can be taken outside the integral. The remaining integral is straightforward and gives us the following result. We can then use this expression to determine the mutual capacitance. As expected, the mutual capacitance depends upon only geometric factors of the capacitor. In this case, it depends upon the surface area of the capacitor and the distance between the two plates. As before, the larger the surface area, the larger the capacitance. This is the equation for the energy stored in the capacitor. It is proportional to the capacitance and the square of the potential difference between the two plates. We frequently say that the electric potential energy stored in a capacitor is stored in the electric field between the two plates of the capacitor. This electric field is, of course, directly related to the difference in electric potential between the two plates of the capacitor. Consider a particle released from rest in between the plates of the capacitor. Initially, the kinetic energy and speed of the particle are both 0. The electric field within the capacitor will exert a force on the particle and will do work on the particle. This work will result in an increase in kinetic energy of the particle. Therefore, we can say that the kinetic energy gained by the particle came from the electric field. In other words, that the electric field stored potential energy. We can rewrite the expression for potential energy in terms of the positive charge stored by the capacitor. This expression indicates that the source of the potential energy stored by the capacitor is the separation of electric charges within the capacitor. A dielectric is an insulator that is placed in between the plates of a capacitor. The molecules or atoms that constitute the dielectric have no net electric charge. In this picture, individual dielectric molecules or atoms are indicated by ovals. When electric charge is separated on the plates of the capacitor, an electric field is created. This electric field permeates the dielectric. We would denote this field as E external. E external will polarize the atoms or molecules that constitute the dielectric. Thus, electric dipole moments are induced in the dielectric, which are then aligned with E external. The induced dipole moments result in a separation of net induced charge, and therefore in an induced electric field. The net electric field is the sum of the external field and the induced field. The magnitude of the net electric field can be determined from the external electric field and the dielectric constant of the dielectric. Dielectric constants are always greater than 1, so the magnitude of the net electric field is always smaller than the magnitude of the external electric field. This makes sense since the induced electric field points in a direction opposite that of the external electric field. The dielectric constant of vacuum is 1. If the magnitude of the external electric field becomes too large, the molecules of the dielectric will be torn apart rather than simply polarized. This is referred to as dielectric breakdown. When dielectric breakdown occurs, the electric charges in the dielectric flow freely as a current between the two plates of the capacitor, and thereby eliminate the separation of electric charge that once existed. Dielectrics are classified by the maximum electric field they can maintain before dielectric breakdown. The dielectric strength is the maximum electric field that can be applied to a dielectric before breakdown occurs. The table below lists the dielectric strength of a few materials.